You know, it is incredibly easy to take movement completely for granted. I mean, think about it for a second. You toss a set of keys across the room to a friend, and they catch them.
Right, yeah.
Your brain just effortlessly calculates the arc, the speed, the exact moment the hand needs to close. It feels, entirely intuitive. It's natural.
Oh, totally. We navigate the physical world all day long based purely on instinct.
Exactly.
Like, we judge the speed of a car before crossing the street, or we anticipate where a tennis ball is going to bounce. We trust our gut.
Right, but when you actually try to write down what just happened, like when you try to mathematically describe that arc, so say a computer or a machine could replicate it,
Right.
suddenly that simple toss becomes an incredibly complex puzzle.
It really does, because the math.
The math doesn't care about your intuition.
Exactly.
But today, we are stripping away that instinct. We have a source text today that essentially acts as the cheat code to that puzzle. We're doing a deep dive into a highly concentrated, incredibly dense framework on kinematics.
And it is dense. Very dense.
Super dense, yeah. But we're going to strip away the intimidating math jargon and give you the exact framework physicists use to predict the future of a moving object. Our mission here is to decode these foundational blueprints and turn them into a highly practical toolkit for you to understand the moving world around you.
What's fascinating here is that to get to that predictive power, this text first demands that we stop trusting our gut entirely, like completely.
Yeah, leave the gut at the door.
Exactly. It forces us to break down movement into measurable objective variables. It establishes a really rigid universal language before we can even begin to claim we understand what motion actually is.
Okay, let's unpack this, because before we can bake the cake, we need the raw ingredients.
Right.
The text lays out that any analysis of motion has to start with 6 specific core variables. So that's time, distance, displacement, speed, velocity, and acceleration. These are the 6 pillars of kinematics.
Foundational blocks, yeah.
Right. Now, for our listeners who maybe remember high school physics, these aren't just synonyms. The text specifically groups them into a strict hierarchy. Scalar metrics and vector metrics.
Exactly. And the text frames this as a really vital hierarchy. Most of our listeners probably know scalars are just amounts.
Like magnitudes, right?
Yeah, magnitudes without direction. So time is just a duration. Distance is just total ground covered. Speed is how fast. They're the baseline reality.
Okay, so just the raw numbers.
Right. But vectors, which have both magnitude and a specific direction, like displacement, velocity, and acceleration vectors, are where causality lives. You literally cannot predict the physical outcome of a system with just a scalar.
Okay, let's ground this with distance versus displacement. Imagine you're going for a walk, and you decide to walk around a massive, perfectly circular park.
Okay, a big circle.
Right. You start your parked car, you put your headphones on, and you walk the entire perimeter. Your fitness tracker says you walked a distance of exactly 3 miles.
Good workout.
Yeah, that is a fact. You expended the energy to cover 3 miles of ground. But because you ended up right back at your car door, your displacement, like your overall change in position from where you started, is 0.
Precisely. And that distinction is huge. To a biologist calculating calories burned, your scalar distance of 3 miles is what matters. They're auditing the energy of the past.
Ah, auditing the past. I like that.
Right. But to a physicist tracking an object's trajectory to predict its future, your vector displacement of 0 is what matters. You haven't actually gone anywhere relative to your starting point. The system's state hasn't meaningfully changed its location.
Wait, okay, I have to challenge this when it comes to speed and velocity.
Sure, go for it.
If I'm driving down the highway at 70 miles per hour, my speedometer just says 70. It is a pure scalar. Why on earth would a physicist care if my car is pointing north or south? Like, I'm still hitting the same speed trap either way, right?
Well, because the universe operates on vectors. It operates on interactions. Let me give you a scenario. Imagine you are an air traffic controller, and you have 2 airplanes on your radar screen. If you only know their speeds, say, they are both traveling at 500 miles per hour, you have a severe problem.
Oh, man. Yeah, I see where this is going.
Right. You have no idea if they are flying away from each other or if they are on a direct collision course. You need their velocity. You need to know that plane A is traveling 500 miles per hour due east, and plane B is traveling 500 miles per hour due west.
Ah, so without velocity, An air traffic controller isn't managing traffic. They're just watching dots randomly exist.
Exactly. Without that directional component, the data is basically useless for predicting an outcome.
Wow. Okay, yeah, without velocity, you cannot predict the future state of the system.
That's it, exactly. And predicting the future state of a system is the entire goal of kinematics. You aren't just observing, you are forecasting.
Which perfectly tees up the final and maybe most misunderstood variable acceleration.
Oh, absolutely misunderstood.
Because we usually think of acceleration as just pressing the gas pedal, just, speeding up.
Hmm.
But because it's a vector, that definition is incomplete, isn't it?
Highly incomplete, yeah. Acceleration is fundamentally defined as the rate of change of velocity. And since velocity includes direction, acceleration isn't just about changing your speed.
Right.
If you are driving your car at a constant unyielding speed of 30 miles per hour, but you are turning around a curved exit ramp, you are accelerating.
Wait, really? Even at exactly 30?
Even at exactly 30, your speed hasn't changed by a single mile per hour, but your direction is constantly changing. Therefore, your velocity is changing. Therefore, you are accelerating.
That is such a crucial distinction. It prevents you from being fooled by simple observations in your daily life. Like if you feel yourself being pushed against the door of your car during that curve, it's not because you sped up, it's because your vector changed.
Exactly. It gives you the precise vocabulary to describe the invisible forces at play.
So it's not just semantics, it's describing reality.
Right. And mastering these 6 terms, time, distance, displacement, speed, velocity, and acceleration, is the absolute prerequisite for everything else we're going to discuss.
Okay, so we have these 6 raw ingredients, like having flour, sugar, and eggs. But how do we actually bake the cake? Like, how do we map this out in the real world?
Well, the source text moves from definitions to applications, starting with the simplest scenario, a perfectly straight line, one-dimensional motion.
Okay, forward and backward, up and down,
No.
but never a combination.
Right. 1D motion is the proving ground. It's where we learn to use the tools of kinematics. And the text provides 3 very specific tools to model this motion: equations, graph, and diagrams.
And this is where my intuition always hit a wall in physics class.
Oh, you and everyone else.
Right. I get the equation and the graph.
Hmm.
Mathematics is the language of the universe. If I have the equation for a car driving down a straight road, I plug in the time, and the math spits out exactly where the car is.
Beautiful, clean math.
Exactly. But free body diagrams, they always felt like middle school doodles to me. Just a box with a couple of arrows. Unless, is the diagram the only one that actually shows the cause of the motion? Like the graph shows the speed, but the diagram shows the engine pushing the car?
If we connect this to the bigger picture, you'll see exactly why the text demands all 3 models. They aren't redundant at all. They compensate for each other's blind spots.
Okay, lay it on me.
Let's look at the equation first. An equation gives you exact numerical precision. It is a flawless predictive engine. You plug in 4.2 seconds. It gives you a position down to the millimeter.
Right.
But an equation is a black box. It's a terrible storyteller. It doesn't let you, see the motion intuitively. You just get an output.
It's just cold numbers. It gives you the destination, but tells you absolutely nothing about the scenery along the way.
Exactly. That is where a graph comes in. A graph reveals the narrative. It exposes the trends over time at a single glance.
So you can just visually map it.
Right. If you look at a velocity versus time graph and see a flat, horizontal line, you instantly know the object is moving at a constant velocity. You don't have to calculate anything. The visual geometry tells you the physical reality.
Oh, wow.
Yeah. And if the line slopes upward, the object is accelerating. The steepness of the slope literally is the rate of acceleration.
And there's that incredible trick with graphs, the area under the curve. Let's really explain why that works mathematically, because it sounds like magic, but it's just pure logic.
It is brilliant logic. Okay, so on a velocity time graph, your vertical y-axis is your speed, say, meters per second. Your horizontal x-axis is time seconds.
Got it.
If you have a flat line representing constant velocity, you essentially have a rectangle drawn on your graph. How do you find the area of a rectangle? You multiply the height by the width.
So you're multiplying the speed by the time.
Yes. And if you multiply meters per second by seconds, the seconds cancel out, and you are left purely with meters distance.
That is, wait.
Yeah. The literal physical area shaded under that line on the graph, mathematically, equals the total displacement of the object. The geometry is the math.
That is wildly elegant. The graph maps the results of the motion perfectly. But returning to my earlier thought, neither the equation nor the graph explains why the object is moving. They just describe what is happening.
Which brings us back to those middle school doodles. Equations and graphs are utterly blind to the physical context.
They just assume the motion is happening.
Right. Let's say your equation says an object is accelerating at 9.8 meters per second squared. Your graph shows a perfectly upward sloping line. That is flawless data. But a free body diagram anchors that abstract math into physical reality.
How so?
Well, the diagram draws the box, and it draws an arrow pointing straight down labeled gravity.
Ah. The diagram is mapping the invisible forces.
Yes. The diagram shows the cause, the graph shows the effect, and the equation provides the exact measurement of that effect.
Man, that's cool.
In one-dimensional motion, using all three of these models together ensures you have zero blind spots. You have the what from the equation, the how from the graph, and the why from the diagram.
When you put it like that, it really does feel like a superpower. You're taking the chaotic, messy variables of reality and placing them into a structured framework.
A completely predictive framework.
Right. If I'm looking at a car sitting at a red light, my diagram shows the invisible forces like gravity pulling down, the road pushing up, the engine force waiting to push forward.
Yeah, exactly.
My graph of velocity sits at 0. When the light turns green, the diagram shows the forward force arrow overcome friction. The graph suddenly slopes up. And my equation tells me exactly where that car will be a mile down the road. I'm practically seeing into the future of that one-dimensional line.
You are. You are no longer just observing the world, you are modeling it.
But life rarely happens on a perfectly straight track, you know.
Very rarely.
1D motion is great for learning the ropes, but the real world is messy. To truly decode the physical universe, we have to look at the next level of complexity, the source text outlines, which is applying these exact same models to infer motion in 2 dimensions.
Yeah, moving from 1 dimension to 2 dimensions is a massive conceptual leap.
Here's where it gets really interesting.
Yeah.
Think about my analogy earlier with the one-dimensional motion. 1D motion is like a train on a track. It has exactly 2 choices. It can go forward or it can go backward in reverse.
Right, it's entirely locked to a single line.
Exactly. But 2-dimensional motion. 2D motion is like a ship sailing on the open ocean. It has its own engine pushing it forward and backward, but it also has ocean currents and winds pushing it left and right simultaneously.
It's operating on an x-axis and a y-axis at the exact same time.
Yeah.
What's brilliant about the foundational text here is that it doesn't introduce a whole new set of tools for the ship. The tools haven't changed. We still use the exact same equations, graphs, and diagrams. But because we are applying them to a 2-dimensional plane, concepts like displacement and velocity become profoundly more complex.
But if the tools are exactly the same, why does the complexity skyrocket? Is it just, like, twice as much math?
It's not just more math, it's a fundamental shift in how we understand reality. In 2 dimensions, horizontal and vertical motions are happening at the same time, yet they act completely independently of one another.
Wait, horizontal and vertical act completely independently.
Totally independent.
That feels incredibly counterintuitive. I mean, if I throw a baseball really hard, it feels like the horizontal force of my throw should somehow fight against the downward pull of gravity. It stays in the air longer because I threw it harder,
Yeah.
right?
Nope. And this raises an important question about how forces actually interact, or more accurately, how they don't.
Okay, I'm listening.
Let's look at a classic physics thought experiment that the text references. Imagine you have a perfectly flat, endless field. In your left hand, you hold a bullet. In your right hand, you have a rifle loaded with an identical bullet aimed perfectly horizontally across the field.
Okay.
At the exact same fraction of a second, you drop the bullet from your left hand and you fire the rifle from your right hand. Which bullet hits the ground first?
Okay, if you ask anyone on the street, their instinct screams that the dropped bullet hits the ground first. Because the fired bullet is traveling so incredibly fast horizontally, it feels like that speed must somehow keep it aloft.
Right. It feels like the forward momentum should just override gravity for a little bit.
Exactly.
But our human instinct says sheer speed matters. The kinematics models, however, reveal the mathematical reality. The equations for the vertical y-axis and the horizontal x-axis are completely isolated.
Why?
Because vectors operating at exactly 90-degree angles to each other share 0 mathematical components. They are orthogonal. The math literally cannot bleed over from one axis to the other.
So a horizontal force cannot alter a vertical force, period.
Period. Gravity is pulling both bullets down at the exact same rate, an acceleration of 9.8 meters per second squared. Gravity doesn't care that one bullet is moving at supersonic speeds to the right.
Wow.
Yeah, the horizontal velocity has absolutely zero vertical component, so it does absolutely nothing to counteract the downward pull of gravity. Therefore, despite the fired bullet traveling hundreds of yards away, both bullets hit the dirt at the exact same instant.
That is wild to visualize. It completely defies common sense. The dropped bullet just falls a few feet. The fired bullet crosses a football field, but they hit the grass at the exact same millisecond.
It does defy common sense, and that is exactly why we need the diagrams, equations, and graphs. Our brains lie to us, the models do not.
Yeah, the map doesn't lie.
A free body diagram would show the gravity vector pointing down identically for both bullets. The huge horizontal vector on the fired bullet is drawn at a 90-degree angle, showing no upward lift.
Okay, I see it.
The equations would prove that the vertical time to reach the ground is mathematically identical. The graph would visually map that terrifyingly fast horizontal trajectory, completely independently from the identical vertical drop.
So by splitting a complex 2D problem into two completely separate 1D problems, an X problem and a Y problem, we can model anything.
Anything.
Going back to the ship on the ocean, if the engine is pushing it north at 20 knots and a bizarrely strong crosswind is pushing it east at 20 knots, we don't have to invent new math.
Nope.
We just track the north vector and the east vector separately and combine them at the end to find the actual diagonal path.
Exactly. You map the cause with the diagram, map the effect with the graph, and get the precision with the equation. You track the X and you track the Y. It's the ultimate divide and conquer strategy for understanding the universe.
So what does this all mean? If we take a step back and look at the journey this framework has taken us on, it's a masterclass in sense-making. It's entirely about taking the chaotic, overwhelming movement of the world around us and placing it onto structured, reliable models.
It really starts by forcing us to abandon our gut instincts and adopt those 6 raw variables: time, distance, displacement, speed, velocity, and acceleration.
Right. We learned that to a physicist, auditing the past isn't enough. Direction matters just as much as magnitude, making vectors like velocity and displacement the true stars of the show because they allow us to predict causality.
And from there, we applied those raw materials to a one-dimensional line. We realized that equations give us exact precision, graphs reveal the narrative of the motion through visual geometry, and free body diagrams map the invisible forces that cause the motion in the first place.
The triad.
Yeah, they are a triad, a team of models working together to eradicate any blind spots.
And finally, we upgraded those exact same tools to map out two-dimensional motion. We unlock the absolute mind bender that horizontal and vertical movements can happen simultaneously without actually affecting each other, because 90-degree vectors share no math.
Such a cool concept.
We built a toolkit to decode the physical universe. But as we always find on this show, there's always another layer to the onion.
Oh, there is always another layer, and it's a layer I want to leave you, the listener, thinking about today.
I tell.
We've mapped the train on the track, and we've mapped the ship on the ocean. We've mastered inferring motion in 1 and 2 dimensions using our graphs and equations. But as you navigate the physical world today, consider this. What happens to these models when we try to map motion in 3 dimensions?
Oh, man.
Think of a drone flying forward, drifting sideways in the wind and accelerating upward all at once. The math holds, but the geometry becomes vastly more complex.
I can only imagine.
And taking it a massive step further, how do our equations and diagrams hold up when we zoom out to a cosmic scale? When we get into astrophysics, where that very first variable on our list, time, is no longer a constant scalar, but something that physically bends and warps depending on your velocity.
Right, relativity.
Yeah, relativity. Our neat little 2D models suddenly face a whole new universe of complexity when time itself refuses to tick at a constant rate.
That is an incredible thought to end on. The idea that time itself isn't safe from the math. From the simple toss of a set of keys across a room to the bending of time around a star, it all starts with those fundamental pillars. Thank you for joining us on this deep dive. As you go about your day, we encourage you to look at the moving world around you through this new analytical lens. Next time you see a car turning a corner or you drop something on the floor, see the vectors, see the independent dimensions, and remember the cheat code you've learned today. Catch you next time.